Welcome to The Explainer. Today we're popping open a totally fascinating historical time capsule to literally unlock the DNA of modern artificial intelligence. We talk about AI like it just dropped out of the sky yesterday, all wrapped up in these super complex chatbots and deep neural networks. But to really get how these systems think, we got to go back, like way back, specifically to August of 1979. And this is a huge deal because the multi-billion-dollar AI industry reshaping our world right now, yeah, it's still playing by these exact same 45-year-old rules.
So, what exactly did the blueprint for artificial intelligence look like 45 years ago? I mean, think about how totally blank the slate was back then. No internet, no massive data sets. We're talking about an era where computers took up entire air-conditioned rooms and honestly had a fraction of the processing power of your smart toaster. Those early computer scientists had to figure out how to teach a machine to solve a problem completely from scratch. They were laying down the very tracks that today's high-speed AI trains run on. And their answers? They're older and way more ingenious than you might expect.
Okay, let's dive into this incredible physical artifact. This is the preliminary edition of the Handbook of Artificial Intelligence, printed way back in August of 1979. It looks like just a simple blue binder with a handwritten sticky note on it, right? But inside these pages is the actual foundational DNA of the technology currently reshaping our world.
Now, this wasn't just some casual weekend garage project. Compiled by top-tier grad students and researchers at absolute powerhouses like Stanford, MIT, and Xerox PARC, this book was a monumental effort. And it's important to grasp the sheer gravity here. It was heavily backed by massive federal agencies like ARPA and the NIH. Their goal was incredibly ambitious. They wanted to comprehensively map out the entire wildly diverse field of AI as it existed right at the dawn of the 1980s.
And man, the pioneers behind this book had an incredible sense of timing. Right there in the foreword, the editors explicitly stated it was, quote, urgent for AI to go public. For 20 years, these researchers had been talking in an echo chamber, mostly just to themselves, in isolated computer science labs. But as computing costs finally started to drop, they realized they needed to get these theoretical concepts out there to a broader engineering and scientific audience. Basically, they knew the revolution was coming.
Section 1. Problem solving is search. Navigating the maze.
So how did they define a computer's ability to think back then? Well, to an AI researcher in 1979, problem solving was fundamentally framed as a process of search. Now hold on, clear your mind of what search means today. We're not talking about typing a question into a search engine to find a web page. In this world, search is the process of navigating a crazy, branching maze of possibilities to find a specific sequence of steps. They call these steps operators, and they're what get you from your starting point straight to your solution. And this concept of search was applied to some incredibly diverse challenges. It wasn't just text. We're talking about solving physical puzzles, proving insanely complex math theorems, calculating the absolute shortest path for a traveling salesman visiting multiple cities, or even mapping out winning chess moves. To the computer, all of those are literally just different flavors of the exact same search problem.
Section 2. The mechanics of search. Building the AI engine.
Let's lift the hood and see how this search engine is actually built. The text breaks a problem-solving system down into 3 elegantly simple parts. First up, you have a database. Don't think of a boring spreadsheet. This is a snapshot of the current state of the world and your ultimate goal. Second, the operators. These are the specific rules that let you actually change that current state. And third, the control strategy. Basically, this is the brain within the brain. It's the system's internal logic for deciding, okay, which operator should I use next to get closer to the finish line?
Let's make this a bit more concrete to see how these operators work in practice. In theorem proving, your operator might be a heavy logic rule, like modus ponens. In calculus, it's a rule to simplify an equation. But in chess, the operators are super tangible. They're literally just the legal rules for moving your pieces. So, moving your knight 2 spaces forward and 1 space over, that is an operator that instantly creates a brand new state on the board, successfully updating that database we just talked about.
Section 3. Forward versus backward reasoning. Directions of thought.
Once the board is set, the AI has to pick a direction to actually think. And there are 2 main ways to do this. Over on the left, we've got forward reasoning. That's data-driven, bottom-up. You start with what you have right now and apply operators step by step, hoping you hit the goal. On the right, you've got backward reasoning. This one is goal-directed. You start at the ultimate finish line and work backward, breaking that massive goal down into bite-sized, easier-to-solve sub-goals. The authors note that humans do this all the time. Think about planning a road trip.
You start with the beach as your destination, and then work backward to figure out which highways are going to get you there. Section 4. The combinatorial explosion, the big roadblock. But here is where these early researchers smashed right into a terrifying mathematical wall known as the combinatorial explosion. Imagine an AI trying to solve a problem using an exhaustive search. That basically means it blindly checks absolutely every single possible sequence of moves just to find the right one. The issue? With every single step, the branching possibilities multiply. The nodes in this search graph grow exponentially. So for anything harder than tic-tac-toe, the maze instantly gets unimaginably massive. To really wrap your head around that sheer scale, the handbook cites a famous estimate for chess. If a computer were to map out every single different complete play in an average-length chess game, it would have to examine 10 to the 120th power different nodes. Think about that for a second. That is a 1 followed by 120 zeros. Just for context, that is vastly more than the total number of atoms in the entire observable universe. No way around it. That's wild. So, the big takeaway here is this. A computer simply cannot brute force its way through a search space that massive. It doesn't matter how fast your processor is, you're gonna run out of time and memory before you even scratch the surface. To achieve real artificial intelligence, the machine desperately needed a shortcut. It needed a way to ignore the bad moves without actually calculating them.
Section 5. The power of heuristics, the clever workaround.
And that brings us to the absolutely brilliant workaround that quite literally saved AI from infinite computation, heuristics. Think about a human grandmaster playing chess. They don't waste brainpower calculating every terrible move, right? Experience tells them exactly which areas of the board to focus on. Early AI researchers realized, hey, we have to program this kind of intuition into the machine. By giving the AI heuristic knowledge, which is basically insider info specific to the problem's domain, the system can zero in its search. It intentionally ignores the mathematically useless paths, dramatically reducing the number of nodes it actually has to calculate.
Check out this incredible quote the handbook pulls from AI pioneers Newell and Simon, dating all the way back to 1957. They defined a heuristic as a process that may solve a given problem, but offers no guarantees of doing so. I really want you to let that sink in. In traditional computer science, you write a program to get a perfect, guaranteed answer. But in AI, you are explicitly programming a rule of thumb. It's a calculated guess.
And honestly, this represents the core philosophy of modern artificial intelligence. Heuristics prevent that massive combinatorial explosion by trading mathematical perfection for practical, everyday efficiency. These heuristic methods were the massive, game-changing contribution highlighted in this 1979 text. They basically proved that for a machine to act intelligently, it didn't need to be perfectly exhaustive, it just needed to know how to effectively navigate the maze. So, as we pack up this historical time capsule, I really want you to take a moment to appreciate the sheer ingenuity of these early blueprints. I mean, we are still using these exact same fundamental concepts, state spaces, operators, heuristics, in the wildly complex AI architectures of today. So I'll leave you with this thought. If these 45-year-old foundational blueprints built the astonishing AI that we rely on right now for everything from medical diagnoses to global logistics, what unimaginable human problems will tomorrow's heuristics conquer? Thanks for hanging out with me on this explainer, and remember to keep questioning the technology around you.